solve two vehicles on that.
Okay, fine. So in today's class, we'll talk about the remaining two standard cases, that is hollow cylinder, the sphere, and the composite cylinder in sphere part. Right. So we have up till now used the approach where the Fourier's law is used in analysis along with the heat conduction equation and the boundary conditions, corresponding boundary conditions, right? So there is one more alternate way by which you can do the similar kind of analysis. That approach we are going to discuss today. Fine. So shall we start with hollow cylinder now?
Yes, sir.
So let me share the slides first. Okay. Can you see my slides?
Yes, sir.
Yes, sir.
Okay, fine. So next case is a hollow cylinder. Now, if you have understood the approach in case of the plain slab or a plain wall, similar kind of approach is used here. So, what is the starting point? So, we will talk about the standard or the general heat conduction equation in cylindrical coordinates first, right? So, there we use the Cartesian coordinate equation. Now, it is the cylindrical coordinate system. So, you just write down this heat conduction equation in cylindrical coordinates in its most general form. So the equation is 1 by r dou by dou r of k r dou t by dou r plus 1 upon r square plus dou by dou phi of k dou t by dou phi plus dou by dou z k dou t by dou z plus q dot. What is this q dot? Q dot is the volumetric heat generation rate. This must be equal to rho Cp dou t by dou t. Note down, this equation is not written in terms of the quantity or the property thermal diffusivity. Reason being, k is considered as a variable with respect to this radius r. That's why r in first term you will find that k is kept inside the bracket, and similarly in the second and third term you will find that the k is also varying with phi and z, right? So k is considered as a variable, space variable here. Fine. Now we are going to simplify this for our case, which is one-dimensional steady-state heat conduction equation in hollow cylinder. I repeat, one-dimensional steady-state heat conduction in a hollow cylinder. The diagram now. So we have the hollow cylinder here. You can draw the diagram quickly. So this is your hollow cylinder. Note down the information which is given. So R1 is the inner radius and R2 is the outer radius of your cylinder. And what is happening here is the hot fluid is flowing through the inner tube in this direction, okay, which is shown here. And the temperature of the hot fluid is T infinity 1, and the heat transfer coefficient from the inner side is H1, heat transfer coefficient. Similarly, you have the another fluid surrounding this tube or a cylinder, which is cold fluid, whose temperature is T infinity 2, and the heat transfer coefficient for the outside fluid is H2, right? And apart from this R1, R2, I already talked about these two notations, inner radius and outer radius. You can use Ri, Ro also, symbols, if you wish to use them. And then the two temperatures are also given. So the inner surface temperature is Ts1 and the outer surface temperature is Ts2. Fine. And apart from these temperatures, the length of the cylinder is noted down as capital L. So this is what the geometrical information for the one-dimensional steady-state heat conduction in case of hollow cylinder, right? Now, if I try to find out what is the temperature distribution in this thickness of the cylinder, this thickness, this portion. So the temperature distribution, the exaggerated view of temperature distribution is shown here. So this is your the radius R1. So this is the radius R2, and in between this R1 and R2, how the temperature is varying. So this curve indicates the temperature distribution in this thickness of the cylinder. Is it clear? So temperature is varying from this Ts1 to Ts2. Fine. Hello.
Yes, sir. So, sir, you want to say that from inner wall to outer wall is the temperature changing? Is there something like that?
Yeah, yeah. So we are going to analyze the case where the heat transfer is taking place along the radial direction, means in this direction, radial direction. Fine. Heat transfer is taking place in the radial direction, outward direction. So we have the three coordinates r, phi, and z. So out of this we are saying that the heat is transferred along R direction. So your temperature is function of R alone. This is what we are going to consider. Is it clear?
Yes, sir.
If you simplify this equation, when I say one-dimensional heat conduction, it means this phi terms will go out, and the z terms will also go out. And then if I say no internal heat generation, then this term will be 0. And if I say steady state, this term will be 0. Correct? So when you make all those assumptions, then you have only one term remaining, this one, first one. And the simplified form of the heat conduction equation will look like this. Now why we are writing the total derivative d instead of dou? Because we know that the temperature is function of R alone and not the function of other variable like T, right? So that's why I'm writing d instead of dou. So 1 upon R d by dr of kr dt by dr is equal to 0. This is our starting point now for the analysis. Now, you can integrate this equation twice because we know this is the second order differential equation, so we have to integrate this twice. Now, I am not talking about the mathematical steps in between. We know this, how to do it, right? If you solve this equation or integrate this equation twice, you will get the temperature distribution equation, something like this. So, temperature as a function of R will be equal to C1 ln R plus C2. So C1 and C2 are the constants which we have introduced once we integrated this equation twice, constants of integration, right? C1 and C2. Now it is time to find out these constants C1 and C2. So you need two boundary conditions for that, right? Now what are those boundary conditions? So using the boundary condition, the first boundary condition, this is your boundary condition 1. So first boundary condition is at R is equal to R1 means the inner radius here. At R is equal to R1, temperature T is equal to Ts1, correct? So temperature at the inner face is equal to surface temperature 1, Ts1. And the second boundary condition is at R is equal to R2 means at outer surface here, temperature T is equal to surface temperature 2. So this is your boundary condition. So if you are not comfortable using this kind of notations, use this. At R equal to R1, T is equal to Ts1, and at R equal to R2, T is equal to Ts2. So when you use these two boundary conditions one by one, what you will get is the equation 3. So first you will get Ts1 is equal to C1 ln R plus C2, and the second equation you will get Ts2 is equal to C1 ln R2 plus C2. So now you have the two equations and two unknowns, C1, C2. Solving these two expressions, you should be in position to find out what is C1. So your constants of integration expressions will look like this. Note down this. So C1 will be Ts2 minus Ts1 divided by ln R2 by R1, and C2 will be Ts1 minus Ts2 minus Ts1 divided by ln R2 by R1 into ln R1. So the constants of integration C1 and C2. Is it clear? Hello. So first you will find C1, because it is easy to find out C. If you deduct one equation from the other, the C2 will get cancelled out, and you will get the value of C1 first, and then just put it back in any of these two equations, and you will get the C2. Very simple. Fine. Up to this point, is it okay?
Yes, sir. It's fine.
Fine. So now the next step is, once you know the constant C1 and C2, you have to put it back to this equation, temperature distribution equation, and what you will obtain is the temperature distribution, how the temperature is varying in the thickness of the cylinder. So this is the expression of temperature distribution. I will write temperature distribution equation. So T as a function of R. So this is not T into R, remember. T as a function of R is Ts1 minus Ts2 divided by ln R1 by R2 ln R by R2 plus Ts2. This is what the temperature distribution equation is, right? You can rearrange the term and rewrite this equation the way you want. Now, I am using the Fourier's law, or Fourier's equation. Now, remember this. In case of Cartesian coordinates, we use Q is equal to minus Ka dt by dx, or rather Qx is equal to minus Ka dt by dx. So this is something to do with the heat transfer along x direction. So here the heat transfer is taking place along r direction. That's why I am writing Qr is equal to minus Ka dt by dr. So if you want few more clarifications about the notations, you can use this A as AR also. If you want to use the notation. But remember, this A is nothing but the area normal to the direction of heat flow. I repeat, this A is nothing but the area normal to the direction of flow. And the gradient, now here the gradient is along x direction, but here the gradient is along r direction. Temperature is varying along r direction. That's why dt by dr is written. You understood? This is again the Fourier's equation or Fourier's law in cylindrical coordinates. I am going to ask these questions, all these questions in oral exam. So this equal to minus K will remain as it is. So this A is nothing but the area normal to the direction of heat flow. Now look at the diagram. So heat transfer is taking place in radially outward direction. So the area of heat transfer is the area when you open this cylinder, correct? When you open the cylinder. So I am taking any radius r here. So at that particular radius r, when I open the cylinder, the area is going to be 2 pi r L, surface area, which is responsible for the heat transfer to take place. Is it clear why area is 2 pi r L?
Yes, sir. Getting it.
Fine. So that's why this A is replaced by 2 pi r L, the dt by dr will remain as it is. Name this as equation 5. The next step is you have to write down the expression for the heat transfer or the rate of heat transfer QR. So QR is equal to 2 pi KL or LK. If you find it easy to remember it as 2 pi KL, write 2 pi KL into bracket TS1 minus TS2 whole divided by ln R2 by R1. Right? So this is the expression which will give you the rate of heat transfer along the radial direction R. Right? So temperature distribution, the first step is to find out the temperature distribution, and second step is to find out the rate of heat transfer. So in between you need the Fourier series, right? Get me or not? So you can write what is the conduction resistance for the cylinder. Now on what basis this equation is written, you can add one more step in between. So we know we used to write the expression as Q is equal to delta T by R total, right? Or RT, thermal resistance. So in similar way I can write this R thermal resistance is equal to delta T by Q. This way I can write, no? Or not?
Yes, sir.
Okay, fine. Or you write the expression in first form, and then whatever is there below the this line or the denominator, that should be R total, correct? So I will write it in this fashion first. So QR must be equal to, in numerator I should write only temperature difference, which is TS1 minus TS2, this temperature difference. Rest all should be written in the denominator. So what I can write in the denominator is, this term will be written in the denominator as 1 upon 2 pi KL, right? Multiplied by ln, this term will remain as it is, R2 by R1, correct? Now, so this is delta T divided by, this term must be R thermal resistance, contact resistance. So this is how this term is written. So the thermal resistance due to conduction for the cylindrical system is equal to ln R2 by R1 divided by 2 pi KL. Is it clear?
Yes, sir. Yes.
Okay, fine. So try to compare this case with the slab. Huh? So what is the thermal resistance in case of slab? Is it L by Ka? Correct?
Sorry, sir. Can you repeat the question?
What is the thermal resistance in case of slab, plain slab? Is it L by Ka?
Yes, sir.
So you should compare the equations of temperature distribution, then the rate of heat transfer, and the thermal resistance for all these three cases, plain slab, hollow cylinder, and hollow sphere. Then and then only you will get the idea how it is. Fine. Clear? Now shall I go to next slide?
Yes.
Okay, now it is time to talk about the composite cylinder. So the same thing I am going to take forward. Only thing is I am going to add maybe 2 or 3 layers to this. Like R1 radius is there, no? So I may add R2, R3, and we'll call it as a composite
Sir,
cylinder. Hmm.
sir, I have a doubt, sir. So why
Yes.
are we taking hollow cylinder only?
Why are we taking hollow cylinder?
Yeah.
So what do you want me to take then?
So can't we take solid cylinder? I mean, filled inside.
Ah, you can take the solid cylinder, but that scenario will be different because nothing will be flowing inside, na? In case of solid cylinder. Hear me or not?
Not completely, sir. Can you elaborate?
Okay. See, if you take a solid cylinder like this, now this is total solid, right? Total solid, correct? It's complete solid.
Yes. Yes.
Now, so then no fluid is flowing inside this tube, right?
Yeah.
Right?
Yeah. Yes. Yes.
So I have only fluid on this side, no? We will solve this kind of problem also. Yeah, this is used for the conductors, electrical conductors. We are going to study this one-dimensional lead conduction in case of electrical conductors, right?
Yes, I'm getting it.
So that time we will use the different approach, right? Okay. Now composite cylinder. Look at the geometry. Now I have shown only the radius and nothing else. So now this time we have the fluid from the inside having temperature T infinity 1 and heat transfer coefficient H1, right? And on outside we have the fluid having temperature T infinity 4 and the heat transfer coefficient H2. And there are 3 regions of this composite cylinder, region A, B and C. And the corresponding radius and the surface temperatures are shown here. So the surface temperature of the inner wall, the surface temperature of the outer wall, and these two are the interface temperatures. T2 and T3 are the interface temperatures, correct? And the radius, R1 is the innermost radius, R4 is the outermost radius, and R2 and R3 are the in-between radius. Clear? Now, so looking at the temperature distribution, it should be clear to you that the heat transfer is taking place in outward direction. No? We are taking this convention that outward radius is taken as positive away from the center. So heat transfer is taking place from inside to outside. Remember this. Fine. So you will see the temperature distribution. T infinity 1 temperature of the fluid on this side, then the surface temperature of the inner wall, then the temperature distribution in this thickness of A, then T2, T3 is temperature distribution in B portion, and the T3, T4, TS4 is in C portion, and CS4 to T infinity 4. This is the convection part on the outer side, right? And then you simply draw the thermal circuit like this. QR is the rate of heat transfer along the radial direction. So you have how many resistances now? 5 resistances. Convection 1, then the conduction 1, conduction 2, conduction 3, and convection 2. 5 resistances in series. So say just note down those resistances. So we know the convection resistance is written as 1 upon HA, right? Convection resistance it is written as 1 upon H into A, right? So what is this A? Area is the heat transfer area available, right? And in case of cylinder, this will be 2 pi RL, we know that. So for inner surface, 2 pi R1 L. So this is A1 basically, the inner surface area. So 1 upon H1 A1. So R convection 1. Then the second is conduction resistance in this. Now how you write the conduction resistance? In last slide we noted down how to write the conduction resistance. So it is ln R2 by R1 means next radius divided by the initial radius. So R2 by R1 ln R2 by R1 divided by 2 pi KL or 2 pi LK. So K is the thermal conductivity of portion A. So 2 pi KL. Similarly, you can write what is the resistance, conduction resistance for part B. So it will be ln next radius divided by the previous radius. So for this thickness, this is the radius R3 divided by R2, this radius, whole divided by 2 pi kb, the conductivity of part B into length L. So L is same for all the radius, you know that. And next is the conduction resistance of portion C. So on similar lines, you will write this term ln Next radius R4 divided by previous radius, which is R3, whole divided by 2 pi kc into L. So conduction 1, conduction 2, conduction 3, then this is conduction 1, and the last one is conduction 2. So what is convection 2? It is 1 upon H4A4, right? And A4 is nothing but the outer surface area, right? So it will be 2 pi R4 L, and H4 is this heat transfer coefficient on the outer side. Is it clear? Hello?
Yes, sir. Clear.
Okay, fine. Now just write down the expression for the rate of heat transfer QR. So what is rate of heat transfer QR? It is the delta T divided by R total, right? So same equation is applied here. So QR is the overall temperature difference, which is delta T, T infinity 1 minus T infinity 4, highest temperature difference, divided by sum of all the resistances. So all these resistances are summed up here, right? So sometimes you will find in case of the cylindrical system, they write this kind of expression, QR by L, and they will call this as Q dash. So this is called as the heat transfer rate per unit length of the cylinder. So this L can be taken on this side, right? Get me or not? Or you can simply divide by L on both sides, and then this L will go out here, and that L can be written on this side, Q by L, something like this. Clear? So this will be called as the heat transfer per unit length, means consider length of the cylinder as 1 meter in that case. Clear? Okay. So we know this, like the overall temperature difference between R total, and this is written in terms of overall heat transfer coefficient UA delta T. So Q is UA delta T. I am using that standard expression where the definition of overall heat transfer coefficient U is required. So UA T infinity 1 minus T infinity 4. Now how we will define the overall heat transfer coefficient U? Now this is not similar to the slab case because in case of slab the area is not varying. Even if you go on adding the layers, number of layers to the slab like this, you go on adding the number of layers to the slab. It doesn't make any difference to area A. Area A is constant everywhere, right? So that's why your overall heat transfer coefficient is based on this area alone, right? There is no other term. Whereas in case of cylindrical system, if you go on adding the layers, this area is varying. This area is continuously increasing, right? So it means you have to, what you can say, the base your overall heat transfer coefficient value on either inner area or outer area. So in this case, you can base it on this area, inner area, or this area, outer area, right? So what we'll do is we will base the overall heat transfer coefficient on inner area, and we'll define it like this. So if U is defined in terms of the inner area or inside area, then this A1 will be replaced by 2 pi R1L, right? And then how your definition of U will look like, note down. So your overall heat transfer coefficient U1, now this is based on inside area. The expression for U1 will look like this, 1 upon, write down this. So same term is there, this term is there. The only thing is when you are saying it is based on inner area A1, see all these terms are divided by these terms. Look at this, 2 pi R1 H1. So this will be divided by 2 pi R1, then this will go out, so only 1 upon H1. First term will evaluate like this. So similarly the other terms will evaluate in this form. So we have to simply divide by 2 pi R1 to this thing. So 2 pi will go, then R1 will go up, then this is how R1 upon K, second term, and then ln R2 by R1 will remain as it is. Similarly for this, ln R3 by R2 will remain as it is. And if you divide this by 2 pi R1,
Sir,
same thing will R1 by K.
sir,
Follow.
sir, for U1, sir, we are following the same formula, right? U equal to 1 by RA. So we are using the same
Exactly.
formula.
Exactly. So we are using. Getting me or not? R total is 1 upon UA, right?
Sir, there is some confusion like 1 by H1, there is some confusion in that. I mean, are we using 1 by, I mean, R1 A1 plus R2 A2 like this are we using here?
No, 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 no. Hello.
Yes, sir, yes, sir, I'm listening.
See, when we are basing this, when your definition of U is based on the inner surface area, it means this U is nothing but U1. Huh? Hear me or not? U1. So if
Yes,
this
sir,
is
inner
U1,
one.
then A is A1. This is how you should read it. Clear?
Yes, sir.
Then you will get this expression. Fine. So note down that equation, U1, it is very important. And now, once you know U1, you can use this condition that U1 A1 is equal to U2 A2 is equal to U3 A3 is equal to U4 A4 is equal to reciprocal of the sum of all the resistances R2 1 upon summation R. This condition you know, right? So based on this, you can write this kind of relation. So it is not needed that you should remember how to place the overall heat transfer coefficient on the outer surface area. Once you make it or base it on inner surface area, simply find out U1, put it here. A1 is already known to you, and use this expression or use this one. U1 A1 is U4 A4. So you know U1, just now you calculated. A1 is known, A4 is known, you can calculate, and this is how you can find U4. Correct? So there is no need to rewrite this kind of expression for U4. The moment you know this, you can calculate this. Is it clear?
Yes, sir. Yeah, yes.
However, if you want to write, you can write similar kind of expression. The only difference you will observe is, so here you are getting 1 upon H1, no? In U2 term, you will get 1 upon H4 here. So this term will get cancelled, right? And you are getting R1 by R4 here. So similarly, you will get a different term here. And instead of, you may get R4 by R1 here, opposite of this. And similarly, the terms in between will change, but the form will remain same. Form will remain like this. For example, ln R2 by R1 is going to remain same. This term will change. So instead of R1, you may get R4 here. R4, 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 something like that.
Yes, sir, now, yes, sir, now got that.
Okay, fine. Now, should I go to next slide?
Yeah, yeah, sir.
So you understood how to find out the rate of heat transfer in case of the composite cylinder, and how to find out the overall heat transfer coefficient if it is asked, right? Now it is time to solve numerical based on whatever we have talked about right now. All this. A pipe carrying steam at 230 degrees centigrade has an internal diameter of 12 centimeter and the pipe thickness is 7.5 mm. The conductivity of the pipe material is 49 watt per meter K. The convective transfer coefficient on the inside is 85 watt per meter square. And the pipe is insulated by two layers of insulation, one of 5 centimeter thickness of conductivity 0.15. All this information is given in the diagram on the right hand side. I am just reading for your reference. And then the another thickness is there having the 5 centimeter value of conductivity 0.48 watt per meter. Right? Now the outside is exposed to air at 35 degrees C, correct? And with a convection coefficient of 18 watt per meter square K. Determine the heat loss for 5 meter length of the cylinder. So length is given, capital L, 5 meter. Also determine the interface temperatures and the overall heat transfer coefficient based on inside and outside areas. So I hope if you have understood the last analysis, composite cylinder analysis, you should be in position to solve this. Clear? Hello.
Yes, sir. Yes, sir.
Okay, fine, solve it. So for the sake of simplicity, whatever temperature notations you have to use it. The inner is given T infinity 1, then the T infinity 2, or you can use our same notation like TS1 and this as TS4. So this will be how we have used the notation TS1, then you want to use it as T1 or T2, T2, T3 as interface temperatures, and then call this as TS4 then. Fine. The surface temperature TS4 and the T infinity 2 is given. You can call this as T infinity 4 also, it doesn't make any difference. Now there is convection happening on both sides of the this tube, inner as well as the outer surface, and there are three layers having thermal conductivity K1, K2, K3, and even the radius are also given. So this is your radius R1, R2, R3 and R4. Solve this, it's very simple. So first you have to find out, determine the heat loss, means QR for the length of 5 meter of the cylinder, and also determining the interface temperatures, means find out this temperature T2, T3.
Sir, we have to only find QR, no? Not QR by L, no? Only QR, right?
QR, because length is given, no? 5 meter they have given. So find out QR only. So I am writing only one formula that should be sufficient for you to solve, and that formula is QR is equal to delta T overall divided by R total. So this formula is enough to solve this. So what is delta T overall? So it is the T infinity 1 minus T infinity 2 temperature, right? Overall temperature divided by R total. You have R convection 1 on the inner side, then R conduction 1, R conduction 2, R convection 3 of layers 1, 2, 3 plus R convection 2 on this side. So thus you have to just put the formulas for the resistances, find out these resistances separately, and then find out R total. Don't put everything in one formula. Hello, follow this practice. Find out the resistances.
Yes, sir. Yes, sir.
So if you miss even one or two values, no, or if you make if you calculate it wrongly, no, then also at least the examiner knows that you have calculated the other things, right? You tell me values of these resistances first. I will write it here one by one. So what is R convection 1? So what is the formula you are using? Is 1 upon H1A1, right?
Yes, yes.
So 1 upon H1 into 2 pi R1L. So whatever value you get, write it here. Then second is the conduction resistance of this layer, layer 1. So how you write the conduction resistance of cylinder? R conduction resistance of the cylinder, this is equal to Ln next radius
R2 by R1.
previous radius divided by 2 pi
KL.
K1L, right? K1L. So similarly for the other two layers. So it will be R3 by R2, 2 pi K2L, and for this layer it will be R4 by R3, Ln R4 by R3, 2 pi K3L, right? And at last you will write the convection resistance of this side. So R convection 2 is 1 upon H2, this heat transfer coefficient, into A2 or A4, whatever you call this outer surface. So that area will be 2 pi R4L, right? Correct?
Yes.
Okay, find out. Now tell me what is Q or QR in watt? Now tell me value of QR, I will write it here.
Sir, I am getting 1.36 kilowatt.
Tell me in what?
1361.35.
1364.
1361.35.
ठीक. What, right?
Sir, right है क्या? हाँ, sir, right है क्या?
I'm going to project the answer. Wait for something. Fine. So this is first part of your syllabus. First part of your problem, that find out the heat loss per 5 meter length of the cylinder, right? Now also you have to determine the interface temperature. So it is time to find out T2 and T3, these two temperatures. Now same approach I am going to use here. Remember, in case of steady one-dimensional heat conduction, this QR is constant, or QR is same for all the layers, right? Correct? So I can apply this equation of QR as delta T by R for any layer, right? Getting me or not? So I can write QR is equal to T2 minus TS1, this temperature difference. I am using this portion 1 now. So I can write T2 minus TS1, right? Or we are writing higher temperature minus lower temperature. So I will write TS1 minus T2, right? We are writing delta T, overall temperature difference. So this is positive I am writing. So TS1 minus TS2, correct? Divided by R of this slab only. So this, what is this R of this slab? It is R conduction 1. R conduction 1 means this. Correct? Now you understood why I am asking you to find out the resistances separately. Hello?
Yes, sir. Sir, how to find TS1, sir? Can you show?
Okay. So what you can do is TS1 is not given. So before that you have to apply this equation to convection part then. Right? So you can write the same expression, QR is T infinity 1 minus TS1 divided by R convection 1, and from this find TS1. Clear?
Yes, sir, got that.
So once you get TS1, put it here and then find T2, right? So next you will write the expression QR is equal to, for this layer now, so the temperature T2 minus T3 divided by R conduction 2, right? So T2 you have calculated here, then you can find T3 from this. QR is same everywhere. So T3 is also known. Next you will use the same expression QR and you will write T3 minus T4. I am writing equation for this layer. T3 minus T4 divided by R conduction 3. So this will give me T4. T3 just now I calculated here. So from this find T4. And now once you know T4, you can cross check. How to cross check? So you will use that equation for the convection on the outer side. So write down QR is equal to TS. We have found this is TS4 and not T4. TS4. Make it TS4. Surface temperature. No? We have used notation TS. So this TS4 temperature minus T infinity 2, this temperature divided by R convection 2, right? And this time you have to calculate QR and check with your QR value which you have used. So TS4 you calculated here, use that value, and T infinity 2 is known, so this part is known, this is also known. So calculate value of QR and compare it with the value which you have used here. So these two values must be same, then and then only your calculation is correct, otherwise that is not correct. So same thing we did in the composite slab case also, if you remember. The method is same. Method of solution is pretty same. Are you getting it or not? Hello?
Yes, sir, I am getting. But sir, The difference between T infinity 1 and TS1 is not very much. I mean, it's
T
very less.
infinity
And TS1, sir.
is not much, no? Correct.
Yes, sir. It's in
That
points
is
only.
that is expected.
So can you project the answer of
Expected.
QR, TS1 and TS2?
I am going to project all the answers, QR as well as the temperature. Look at this. See, Q result is 1234 watt and not 1361. Or I may be wrong. If all of you are getting 1361, that's fine.
No, sir. 1234 point.
Name yourself.
1234.95 sir आ रहा है.
Who is getting this? Name yourself.
Harshal sir.
Harshal.
Yes.
So this value is correct. Abhishek, you check your calculation. Something is wrong in this.
Yes, sir. Yes.
Fine. So that's why, what you can say, don't be in a hurry while solving this type of problems. Solve it step by step. Even if you make mistake, maybe at the step 2 or 3, then everything will go wrong thereafter. So solve it carefully. Harshal, are you getting this overall heat transfer coefficient value? How to calculate it?
Yes, sir.
How you calculate it? Tell me. Which formula you have used? QR is equal to? Is it same?
Yes,
This formula?
sir. इससे ही try कर रहा हूँ.
Or you can use that formula which we have derived for U1, and from that also you can find out and cross check. The inner, the oral heat transfer coefficient based on inner surface area is 3.35. This is TS1, this is TS4 as per our notations. Hello. Are you getting UA value?
Sir, correct. Sir, I'm trying.
Harshal.
Yes, sir. Just a minute trying.
Hello, sir.
Yes, sir.
Sir,
3.35 आ रहा है.
so I got the U inside, sir. It's same as given on the slide.
Okay, but have you used this formula? QR is U1 A1 T infinity 1 minus T infinity 2, or you use that one which we
No,
have
sir.
derived?
The formula that you have mentioned on the screen, sir. I have used only that.
Okay, same. Fine. Once you know UI or U1, then you can find out this UO or U4 also. No? The way I explained it before. So A1 U1 is equal to A4 U4, right? So check other value, outer surface area, heat transfer coefficient based on outer area. Is it 1.2? Check.
sir, I have calculated of U outside, sir. So it's same as mentioned on the screen. One
Fine,
point, I'm getting 1 point.
fine. So find out interface temperatures. Interface temperatures.
So, sir, you asked for some area, na?
No. Interface temperatures. This is okay. Orally transfer coefficient is okay now. Go ahead and find out interface temperatures the way I explained it before. Arshal.
Yes sir, temperature सब same आ रहा है, almost
सब same आ रहा है? Very good.
point का difference है.
Now have you noticed this thing? Look at the temperature difference between TS1 and T2. It has direct connection with the thermal conductivity of that material. So the thickness of this layer 1 is hardly 0.0075 meter, right? 0.0075 meter. And the thermal conductivity is very high, 49 watt per meter cubic. That's why you see only the temperature difference of 0.1 degrees. There's very less resistance is offered for the heat, or not? Are you getting my point or not? Now, if you look at the middle layer, whose thermal conductivity is 0.15 watt per meter K, and see the temperature drop from 222.2 degrees C, all temperature is dropping directly to 77 degrees. Now, why does this happen? Because the thermal conductivity of that layer is very low, so it is offering very high resistance to heat, or not?
Yes sir.
Fine. Now, shall I go ahead? Now, what we did up till now is we used one typical kind of approach where we started with the heat conduction equation, then its simplification using the assumptions, and then we used the boundary conditions. First we found the temperature distribution, then we used the Fourier's law, and then calculated the rate of heat transfer. This is what we did in last two cases, right? Plain wall and the hollow cylinder. Now we'll see one more alternate approach. So what is this? We use the standard approach. Here we started with the heat conduction equation, then we used the boundary conditions to find it. We used the Fourier's law to calculate the rate of heat transfer. So these three steps we have followed up till now. So this approach is called the standard approach of analysis. Fine. Hello.
Yes, sir. Yes, sir. Yes, sir.
Now we are going to introduce the alternate approach to this. So integral approach we are going to talk about. So what is alternate conduction analysis? Alternate conduction analysis is this. We will use only Fourier's law of heat conduction and nothing else. So we are not going to use the boundary conditions directly. We'll use only Fourier's law of heat conduction. And what we'll do exactly is we are using the fact that this Q, the rate of heat transfer Q, remains constant. I have been talking about this Q remaining constant, Q same through all the layers, right? So we will use this for our benefit. So Q remains constant even though the area varies with position. So where this area is varying with position in case of cylinder, not in case of slab, right? A is same in case of slab, but it is varying in case of the cylinder. Or if you take sphere, then also it will vary, right? And the thermal conductivity K is function of temperature. So we can take into account these two things, and we'll see how this alternate approach of analysis works out. Fine. But this time we have already covered the plane wall and the cylinder thing. So we will try this approach for the third case, which is the hollow sphere. And the same can be used for plane wall approach, can be used for plane wall as well as the hollow cylinder. So I leave it to you to explore it once we use this approach for the sphere. And the first approach you can use for hollow sphere also, right? So that exercise also I leave it to you to explore further. Is it okay? Hello.
Yes, sir. Chalega.
Okay, fine. An alternate conduction analysis continued further. So look at the geometry now. So I am taking any arbitrary geometry like this, and the coordinate system, see x, y, z, any random coordinate system I am taking. So this is your phase 1, which has got the temperature T0, and the area of this phase is A. And why A is function of x? Because along x, this is continuously varying, the area is continuously varying, right? And the outer surface of this geometry is insulated, so adiabatic surface. So typically the conduction will take place in this direction only, along this direction. Are you getting my point or not? So this peripheral area is insulated, and we have the second phase here, whose area is, you can call this as area A1, right? And this is located at distance x1 from this, and qx is the rate of heat transfer along this x direction, which is shown here, right? And the temperature of this phase is T1. So here it is T0, and at the end phase it is T1. So this is what our geometry is, right? Now I am taking any random ring like this, ring-like structure at a distance x from this starting point, right? And the thickness of this strip is dx. So I have shown it here. Dx is the thickness of the strip. So the heat transfer which is taking place in this element is qx from this side, and what is going out is the qx plus dx. So this x plus dx thickness is added here. So this is qx, and the one which is going out is q at phase x plus dx. So this phase is located at x plus dx distance from the starting. So q at x plus dx. Now, do you remember after some time, before some time we said that this qx is constant, right? So qx is same. So what I am going to do next is I am going to equate these two quantities, right? So I am using the standard expression that qx is minus k dt by dx, right? I am using the standard expression minus k dt by dx. So this k is written as function of temperature. That's why you see this kt, right? So I am using the variable separable method here. So on left hand side I am writing qx, and as this phase is located at a distance x, I am integrating this quantity dx upon, now why a is taken on this side? Because a contains this x term, a is function of x, so it is written as dx upon a or ax, right? And this is evaluated, integral is evaluated with the limits x naught means this phase to this phase, so x naught to x. So x is varying, x naught to x is equal to minus, now on the right hand side we have the integral of with respect to the temperature T. So K is function of temperature, so I have kept it KT into dt, variable separable method. And how this temperature is varying? From this phase where the temperature is T0 to this phase where temperature is T. I don't know where this phase is located, that's why I am taking temperature T, any temperature T, right? Is it clear? This is simply the variable separable method. Now, have you understood this formula? Then we'll go ahead. So why we are writing it like this? We are taking any random ring at distance x. Now the cross-section area that A may be a function of x. That's why I'm writing ax, may be a function of x, and the material thermal conductivity K may be function of temperature T. That's why I'm writing KT. Okay?
Sir, why this ax is in bottom? I mean in the denominator.
See, this is multiplying on the right hand side, na? So when I take it on left hand side, it will be divided by, correct?
Yes, sir. Got that, sir. Yes, sir.
So this is variable separable, nothing big in this. Now, second point, integration from a point x naught means this point at which the temperature T naught is known. So this will be known to you, temperature T naught. The resulting equation provides the temperature distribution Tx. So if I know the temperature at this phase, I can take this ring at any distance x, known distance x from this phase, and then I can simply find out what is this temperature distribution. I can find out the expression for this. Is it clear? Now, if the temperature, so this is one part, that you can find out the temperature distribution at any location x, known location x. Now, if the temperature T is equal to T1 at this location is known, let us say. Now, what is known as temperature T1? So, if the temperature T equal to T1 at some distance x is equal to x1 is known, then integrating this equation from x0 to x1 will provide me the expression for Qx. So, then I can find out Qx simply. Right? So, what I know is the temperature at this phase and this phase. I also know the what is x0 and x1. So T0, T1 is known, x0, x1 is known. So I have the limits of both the integrals. Then what is unknown is only Qx. So I can find out Qx. This is how the rate of heat transfer Qx is calculated. Are you getting my point or not? Hello. So this is integral approach considering the variable separable method. Now should I go ahead? Hello.
Yes, sir. Shall I?
Now this note is worth mentioning that this approach should only be used for steady state one-dimensional heat transfer with no internal heat generation. So this approach should be used for one-dimensional, one part, steady state conduction, and with no heat generation. So this Q dot term should be absent. Then and then only this approach will work out, otherwise not. I'm going to ask this question in oral when this will be applicable. Now, should I go to next slide? Okay. Now we'll analyze the case of hollow sphere using this approach. So look at the alternate analysis method. So this time I have shown only the hollow sphere in 2D. So the radius, inner radius is R1, outer radius is R2, and I am taking any random radius R from the center, right? So the temperature at this location will be T, right? And TS1 is the inner surface temperature and TS2 is the outer surface temperature. Same thing. And this is the ring whose exaggerated view I am showing here. Ring having thickness dr. As this is cylindrical system, spherical system, thickness will be dr. There it was dx. So qr is the rate of heat transfer in this direction entering this phase, and qr plus dr is going through this phase. So these two must be same. This is what I am saying. So qr is equal to minus k dt by dr. I am using the Fourier's equation. So minus k. Now what is the area? Area is the surface area available for the heat transfer. So in case of sphere, the surface area will be 4 pi r square at this location. 4 pi r square. So this A is replaced by 4 pi r square. And now I am using the variable separable method. So qr is constant. I have been saying this again and again. qr is constant. So qr is not going to depend on r. So this approach now. So use the variable separable method. So I am writing qr divided by this term 4 pi on this side. So qr by 4 pi, and then integral r terms I am taking on the left hand side. So dr upon r square. This r square will go on left hand side. So and the limits will be r1 to r2. dr upon r square. This must be equal to minus k is considered as a variable of temperature T. So it is kept inside the integral. So k dt by k into dt. And the limits are Ts1 to Ts2. So right from inner phase to outer phase. So I am using the integral for this entire range. So instead of using up to radius r, I am using these limits for entire range because I know the limits. Fine. So now if I assume that k is constant, k is not varying with temperature, so this k can be taken outside the integral. And this is how you can write the final expression for the rate of heat transfer. After solving this, now I am not writing the steps in between. You can use it simply. You know what is the integral of 1 upon r square. You know how to write all that stuff and put the limits of the integral. And finally, you should be in position to derive this equation. Qr is written as 4 pi k Ts1 minus Ts2 divided by 1 upon r1 minus 1 upon r2. Now, if I want to write this equation in the familiar mode, like we write it delta T by R total, right? Or R thermal. So the same expression I am going to write it as Ts1 minus Ts2 divided by this term I will write 1 upon 4 pi K, this term in the denominator, into bracket 1 upon R1 minus 1 upon R2, right? So this is how I am going to write it. Fine? Is it clear? So you will get the value of the thermal resistance of conduction for sphere as 1 upon 4 pi K, 1 upon R1 minus 1 upon R2. So just note down this and we will stop. Running out of time. Write down this, we will stop.
Yes, sir.
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 Just a minute.